In Chapter 5, Section 2, we move on to systems of equations in 3 variables, systems of linear equations specifically in 3 variables. I want to encourage you that if you did not stop and do the practice and get comfortable with 5.1, do that now before we tackle 5.2. You're going to be using the same techniques you used in 5.1, but we're going to do them at another order of magnitude. We're adding in another layer that you have to simplify through. So the more comfortable you are with adding and using substitution, the better off you're going to be coming into this section. So if you are not comfortable with the 5.1 material, stop and get comfortable with that now and then come back. I also want to put your mind at ease that we are not going to be graphing 3 variable systems of equations. Okay, when I'm looking at a system of linear equations in 3 variables, I mentioned this in 5.1. The solution set is going to be all the ordered triples of real numbers, and those ordered triples are going to look like x, y, z ordered triples that satisfy all equations in the system. Now, because instead of just x and y, I've added a z, I've added another axis into my graph. This is going to require a 3D coordinate system with a z-axis through the origin of the xy coordinate plane. Okay, here is kind of what that looks like. Now, it's going to be a little difficult to get this, I'm afraid, on video, but here we go. In real life, this is a little bit easier for me to show. I've got my XY coordinate plane. This is exactly what you are familiar with. When I have XY coordinate plane, I have length and I have height. I have, think 2-dimensional shapes. Think a square or a triangle. It's 2 dimensions. I have length and width. If I want to, I can find area, but it's 2-dimensional, so it doesn't have volume. However, when I go to a 3-dimensional coordinate plane, I'm moving into 3 dimensions. So where I had the XY coordinate plane on a flat surface, now I have a z-axis, and that's kind of hard to see, but there it is, coming right at you. I have a z-axis that goes perpendicularly into that XY coordinate plane. So it comes out into 3-dimensional space. This z-axis comes out into 3-dimensional space. So now instead of just having a square, I have a cube. I have a shape that has length, width, and height. I can find not just area, but I can find volume in 3-dimensional space. So if I wanted, for example, to locate the ordered triple 2, 3, 5, I would move to a positive 2 on the x-axis. I would move to a positive 3 on the y-axis, but then I would have to move to 5 on the z-axis. So I'm out here in 3-dimensional space, not on a 2-dimensional flat surface. Okay, now again, I'm not going to ask you to graph in 3-dimensional space. I'm just trying to let you get a picture in your head of what we're dealing with. That being said, I've provided you some pictures. When I have linear equations in 3 variables, remember we're still sticking with linear equations, my solutions still come in the same 3 possibilities. I have one solution, no solution, or infinitely many solutions. If I have one solution that shows up as a single ordered triple, where I have one solution, it looks like this. You can see my 3 planes that have been graphed, and they intersect at just that one point. Now, one solution doesn't always look exactly like this, but you're going to have 3 planes because each equation in 3 variables is graphed as a plane. The graph of each equation is a plane, not a line. There's one equation, there's a second equation, there's a third equation. This is a way that those 3 equations, those 3 planes, intersect at just a single ordered triple, a single point, x, y, z. Just like in my 2 variable systems, this would be an independent, consistent system. My next option is that there's no solution. There's just no place where all 3 planes intersect at the same time. That could look like 3 parallel planes, or it could look like a situation where 2 of the planes intersect, but not all 3 in any one location. So no solution means no single point exists in all three planes. No single point exists in all three planes. So this is an inconsistent system. And then my final option is infinitely many solutions, where there is a place that exists in all three planes, and that shows up as a line. So all three planes intersect on a line. That line is the solution set. This system is dependent because there's infinitely many solutions. It's consistent because we have solutions. Just like for two variable systems, if I have a solution to the system, that means that ordered triple, that point, has to exist, has to be true for all three equations. So if I check to see if this ordered triple x, y, z, and remember it's always alphabetical order, so it's always going to be x, y, z. I check to see if this ordered triple x, y, z is a solution to my system. I have to check it in all three equations. I have to plug x, y, z in for all three equations. So let's go ahead and do that. X plus y plus z equals 4 would be 2 minus 3 plus 3 should be 4. Well, 2 minus 1 plus 3. 2 minus 1 is 1. 1 plus 3 is 4. It's true for the first equation. Let's look at the second equation. X minus 2y minus z equals 1. Well, x is 2. Minus 2 times negative 1 minus 3 should be 1. 2, and then this becomes plus 2. So the 2 plus 2 is 4. 4 minus 3 is 1. 1 equals 1. That's true. It works in the second equation. So now we have to check the third, because if it's going to be a solution to the system, it has to satisfy all equations in the system. So 2 times x would be 2 times 2. Minus a negative 1 becomes plus 1. Minus z would be minus 3, should be negative 1. Let's see if this is true. Well, 4 plus 1 is 5 minus 3 does not equal negative 1. So this is not a solution. That ordered triple we were given is not a solution, because even though it satisfies two of the values, two of the equations in the system, it does not satisfy that third equation. All right, let's look at our next page. Our next page says we are going to be solving systems in three variables. Okay, you are not going to learn any new methods. We're going to use the methods that we use to solve two variable systems. We're just going to apply them to our three variable system. We're going to reduce the system to just two equations and two variables. When we were dealing with two variables to start, we reduced it to 1. We have to start with 3, so we have to reduce it to 2. The way we're going to do that is look for the easiest variable to eliminate, and we have to eliminate it twice. We're going to use our addition and substitution method to eliminate it from two pairs of equations, so that I have created a system of two equations and two variables, a reduced system. I'm going to solve that reduced system of two equations and use those values to plug back in and find my third variable. Now, it sounds a little bit complex. It's really not. It's just keeping track. We have an original system here. Oh, and then finally you check to make sure it works. My math lab usually does our check for us, right? Okay, so I have a system of three equations and three variables, x, y, z. I want to find the easiest variable to eliminate. I could make arguments to eliminate x, eliminate y, or eliminate z. There isn't one variable in this system that's any easier than the others. You could approach it from multitude of different ways. We're going to do the same thing together so that you have a good couple of examples in your notes. But remember that you can go, like I could decide to eliminate the x, you could decide to eliminate the y, and your friend could decide to eliminate the z, and we all get the same correct answer. I'm going to decide that together we're going to eliminate the y. because when I look at the y's, I see I've already got one that is negative, so it makes it a little bit easier. Now I need to eliminate the same variable twice from two pair of equations. I'm going to start by pairing up equations 1 and equations 2 because I don't have to change anything. When I add those together just like they are, y is going to add to 0. So let's come off to the side and let's copy down the first equation and the second equation and add those up to create what is our fourth equation. Because we've got 1, 2, 3 original equations in the system, we're creating a fourth equation. This fourth equation is going to have only 2 variables because we're eliminating the y. X and 3x is 4x. My y's add to 0, that was my goal. Negative z and positive 3z is plus 2z is equal to negative 2. That is my fourth equation. 4x plus 2z equals negative 2. It only has 2 variables, x and z. So I go back to my original system and I say, all right, I paired up 1 and 2 to eliminate y. I need to pair up either 1 and 3 or 2 and 3 and eliminate y again. Well, it looks like I'm going to choose to do 2 and 3 because I've already got a negative y here and a positive y here. If I take equation 2 and multiply it times 2, I get negative 2y, and then I'm going to add that to equation 3, which has positive 2y. So I'm not changing equation 3. I'm just copying it down. I am changing equation 2 by multiplying it by a positive 2 so that my y's will add to 0. So this becomes 6x minus 2y plus 6z equals negative 4. All right, I'm going to add those two together, and when I add them together, I'm creating a fifth equation, and it's going to have no y variable. That was my goal. So I get 7x plus 3z equals negative 5 as my fifth equation. You see, equations 4 and 5 are just in terms of x and z. We know how to solve equations with 2 variables. So I have a reduced system of 2 equations and 2 variables, and this is what I'm looking at to solve. I have a choice now. I can use either substitution or addition. Substitution is going to give me fractions, so we're just going to use addition. I'm going to rewrite my 2 equations, my system, next to each other, just so I can compare them a little easier. You don't always have to rewrite here. You could just figure out what you need to do to make things happen. But so since this is our first time through, I'm just totally rewrote these 2. I need to decide what variable I'm going to cause to add to 0. 4 and 7, I'd have to go to 28. Don't want to do that. 2 and 3, I can go to 6. That one works. Let's do that. So to get my z's to add to 0, I will multiply this first equation by 3 and my second equation times negative 2, because that'll give me a positive 6x and a negative 6z, not x, a positive 6z and a negative 6z, which will add to 0. Let's rewrite our equations. Make sure you multiply that coefficient to the constant as well. All right, I've created an equivalent system. I'm going to add them together. 12x minus 14x is a negative 2x. My z's add to 0, that was my goal, is equal to 4. So when I divide by negative 2, I get that x is negative 2. X is negative 2, that's my first value. Okay, I'm going to take this negative 2, where x is negative 2, I'm going to plug it in to either equation 4 or 5. Equation 4 or 5 to solve for z. I'm going to choose to plug it into equation 4. It really doesn't matter, but I'm going to choose to plug it into equation 4. I'm plugging in negative 2 for x. So that's 4 times negative 2 plus 2 times z equals negative 2. That's my equation 4 right there. I plug in -2 for x. That gives me -8 plus 2z equals -2. When I move that -8 over, it becomes positive. So -2 plus 8 is 6. Divide that by 2, and I get z equals 3. So I have x, I have z. Now I have to go all the way back to the beginning, to one of my original equations, 1, 2, or 3. And I'm going to take my value for x, my value for z, I'm going to plug them both in and solve for y. That's my remaining variable that I don't know. Well, equation 1 has the lowest, the smallest coefficients. Equation 1 is x plus y minus z equals 0. So I'm going to plug in -2 for x. I don't know y. I'm going to plug in 3 for z. So that's -3 equals 0. Y minus 5 equals 0 means y is 5. And my ordered triple that is the solution to this system is x, y, z. Always make sure you put them in order. That's my solution to this system. This 3-variable system is consistent and independent. It has a single ordered triple as its solution. All right, the key for solving, staying organized. Make sure that you eliminate the same variable twice. And then you're just solving a system of 2 variables. And once you get those 2 variables, you plug back into the beginning to get the third. Let's do another example. Okay, let's go through this second example. We're going to use the same process, the same set of steps. I have 3 equations, equation 1, 2, 3. It's easier if you number them so we can talk about them as 1, 2, or 3. I want to pick a variable to eliminate. We eliminated y last time in the last example. Let's choose z this time. So I need to create equations 4 and 5 that do not have a z. They just have x and y. I'm going to start because -z, positive z adds to 0. So I'm just going to pair up equations 1 and 2 as they are. And I'm going to add those 2 to create my 4th equation. My 4th equation is just going to have x and y because my z's add to 0. Now, again, there's no magic in starting with z. I could have eliminated x. I could have eliminated y. Doesn't make any difference. You just pick a way to go. This looked like the easiest path for me, so that's the path I chose. Now, I paired 1 and 2 and eliminated y. I need to go back and pair again. I eliminated z. I paired 1 and 2, eliminated z. I need to go back and pair up either 1 and 3 or 2 and 3, eliminate z again. Well, equation 1, z is already negative, so I'm going to pair 1 and 3. I'm not going to change 3. So I'm eliminating z. This is a positive 2z. This is already negative. I need to make it a -2. So I'm going to multiply times 2 to this first equation. That gives me my opposites to add together for my z, so that z will add to 0. So I get 4x, equation 5. This is my equation 5. 4x plus 5y is going to be 24, positive 24. All right. Now I'm going to combine equations 4 and 5. And I want to add them, this is my reduced system with just x and y. I want to add them together in such a way that one of my 2 variables, x or y, adds to 0. Well, this is pretty simple because I have 4x for both of them. I just need to make one of them negative. Let's make equation 5 a negative 4x. So I'm going to multiply equation 5 by a -1 times a -1. That's just my little notation to tell me what I'm doing. Equation 4, I'm not going to change anything. Equation 5 becomes -4x minus 5y equals -24. When I add equations 4 and 5 together, My x's add to 0. I get y equals 4, and I've solved for y. Okay, I take that value for y, and I have to plug it into either 4 or 5 to solve for x. Does not matter which one. Let's plug into 5. So we're going to come over here, and we're going to say 4x plus 5 times 4, because y is 4, equals 24. So I have 4x plus 20 equals 24. 4x equals 4 when I subtract 20 from both sides. So x is 1. Now I know x and I know y. I have to solve for z. To solve for z, I go back and I plug in these two values into one of my original 3 equations. There does not matter which one you pick. I always pick the one with the smallest coefficients just because it's a little simpler. So number 1 has the smallest coefficients. Number 1, equation 1 is x plus 4y minus z equals 20. I know that x is 1. I know that y is 4, and I'm looking for z. So 1 plus 8 is 9 minus z equals 20. If I subtract 9, 4 times 4 is not 8. 4 times 4 is 16. I'm sorry. 16 plus 1 is 17. Haha, glad I caught that. 17 minus z is 20. So I get negative z is equal to 3 when I subtract that 17 from both sides. Well, I don't need negative z, I need z. So I'm going to divide both sides by negative 1. Z is negative 3. All right, I have my 3 individual values. I'd have to write it as an ordered pair to get my solution set. X, Y, Z in alphabetical order. 1, 4, negative 3. So it doesn't matter what order you find them in. When you list the ordered triple, you always put it in alphabetical order. Okay, let's do another example. Now I've got 2 examples on this page. We're going to have to squish a little bit to try to make sure we don't run into our space for our second example. I'll try to condense it a little bit, make sure I delineate how much space I have there. Now I'm going to encourage you on this one to maybe stop the video, work it through on your own and see how you do so that you aren't just following along with me. You have 2 good examples to review. Try this one on your own and then come back. Remember, if I choose to go away, you don't go. That's fine as long as we get the same answer. I will give you a tip. I think I'm going to eliminate y again this time. I think I'm going to eliminate y. So I'm going to multiply equation 1 by 2 and add it to equation 2. This gives me equation 4. And then I'm going to go back and I'm going to add equations 2 and 3. And I'm going to multiply 3 times a negative 1. That gives me equation 5 as negative x plus 2z equals 0. So equations 4 and 5, this is a really good opportunity to use substitution because I can solve this for x pretty easily. I can say that negative x equals negative 2z, so x equals positive 2z, and I can plug that in over here and use substitution. So equation 4 becomes 9x plus 3 times 2 oh no, I'm just set it up the wrong way. Let me do this again. I'm plugging in for x. So 9 times 2z plus 3z equals 21. 9 plus 2 times 2z plus 3z equals 21. That's my substitution. So I get 18z plus 3z equals 21. Well, 18z and 3z is 21z. So z is just 1. Z is 1. Okay, I can take this value for z and plug it into either equation 4 or 5. Let's do equation 4. Equation 4, 9x plus 3 times 1 equals 21. 9x plus 3 equals 21. If I subtract 3, I get 9x equals 18. So x is 2. So I know that z is 1, x is 2. And now I need to take both of those, plug them into 1, 2, or 3, and solve for y. I'm going to choose equation 2 this time. We haven't done that. X plus 2y minus z equals -1. Well, x is 2. I don't know y. Minus z is -1 equals -1. 2 minus 1 is 1. So 2y plus 1 equals -1. I subtract that, and I get -2. So I have 2y equals -2, which means y is going to be -1 when I divide both sides by 2. Don't forget to write your solution set as an ordered triple. X, y, z. There's my solution for that 3-variable system. Okay, one more 3-variable system to walk through. And then we have a little bit different look to an equation that we want to talk about. 1, 2, 3. 3 equations. We are going to pick a way to start. I'm going to eliminate y again because that's simple for me. You could do x, just make it different ones negative. You could do z because you've got these negatives right here. In fact, you know what we just did y. Let's not do y again. Let's do z. Let's just eliminate z. Let's start with equations 2 and 3 because z's are already opposite. I don't have to do anything to make that happen. So when I add that together, I get 2x plus y equals 12 as my fourth equation. 2x plus y equals 12. Now I need to create a fifth equation where I eliminate z again. I'm going to choose to add equations 1 and 3. I added 2 and 3 together. I can either do 1 and 2 or 1 and 3. I'm going to do 1 and 3 and multiply the first equation by a positive 3. So I get 3x plus 3y minus 3z equals 5. My third equation doesn't change. And I add. And my fifth equation becomes 4x plus 2y, z's add to 0, equals 8. So I have these two equations, equations 4 and 5, that I need to add together in such a way that one of my variables adds to 0. Let's make our y's add to 0. So if I take equation 4 times a -2, that gives me -4x minus 2y equals -24. And I'm not going to change equation 5. Equation 5 just stays 4x plus 2y equals, ooh. When I look at that, I go, ooh, I got something going on. My x's add to 0 and my y's add to 0. So I get 0 equals, and then this would be a -16. Well, 0 does not equal a -16. So at this point, I have to stop and think, did I make a mistake? No, I did not make a mistake. If I didn't make a mistake and I get a statement that is not true, then I have no solution. So I would give it as the empty set. Okay, one final example in this note set from 5-2. This is just a little bit different way to approach it. So we're going to set this up and solve it together. It says to find the quadratic equation, and that quadratic equation is going to be in the standard form or general form for my quadratic equation. Y equals ax squared plus bx plus c. So my answer is going to be a quadratic equation. Y equals something x squared plus something x plus something. I'm solving for a, b, and c. The graph of this quadratic equation, this parabola, passes through these 3 points. So I'm given 3 different xy ordered pairs to plug in the xy's to get my 3 equations in my system. That's what I'm doing. I'm using each point to write an equation, plugging in my values for x and y, and solving this system for a, b, and c. A, b, and c are my variables this time instead of x, y, z. So for the point 1, 4, this is x, this is y. So ax squared plus bx plus c equals y. This is my y, and x is 1. So this equation, equation number 1, is 4 equals, well, 1 squared is just 1. So a plus b plus c. That's my first equation. Then my second equation, I plug in for x and y. Y is 1 here, x is 2. So my second equation becomes 1 equals 4a, because 2 squared is 4, plus 2b plus c. My third equation, again, I have an xy ordered pair. Y is 4 here, x is 3. My third equation out of my system is 4 equals 9a plus 3b plus c. Now there's my 3 variable system with my variables a, b, c. You know how to solve a 3 variable system. I want you to give it a shot, see what you come up with, and then start the video again and see how we did. I'm going to choose to eliminate b. I'm going to use this first equation paired with 2, and then the first equation paired with 3 to eliminate b. So I'm going to do 1 and 2, and then I'm going to do 1 and 3. If I multiply my first equation times a negative 2, I get negative 8 equals negative 2a minus 2b minus 2c. And then my second equation is just 1 equals 4a plus 2b plus c. I'm going to add those two together. And then my second pair, 1 and 3, I'm still eliminating b. That's what I'm working on. So I need to multiply my first equation times a negative 3. And I add that. And my fifth equation becomes negative 8 equals 6a minus 2c. So there are my 2 equations that I need to combine. And when I do that, when I combine 4 and 5, it would be easy to do c. If I multiply equation 4 times a negative 2, that gives me a positive 2 here. So times a negative 2 gives me a 14 equals negative 4a plus 2c. I'm not changing my fifth equation. And I add those together, and I get 6 is equal to 2a, and then that adds to 0. So a is 3. And I found one of my variables. Sorry, I wasn't showing you guys my work. So I've got that a is 3. I'm going to take that a is 3 and I'm going to plug it into equation 4. Let's plug it into equation 4. So equation 4 says negative 7 equals 2 times a minus c. So I've got negative 7 equals 6 minus c. So subtract 6, negative 13 equals negative c. So c is equal to a positive 13. I've got a, I've got c. I now need to substitute in and solve for b. I can sub in to any of my first three original equations, 1, 2, or 3. Let's use equation 2. Equation 2 says 1 equals 4a plus 2b plus c. Well, a is 3, so 1 equals 4 times 3. I don't know b, and c is 13. So 1 equals 12 plus 2b plus 13. So 1 is equal to 2b plus 25. If I subtract the 25, I get negative 24 equals 2b. So b is negative 12. So I have a, I have b, I have c. And remember at the beginning I was told that my solution was going to be an equation that looks like this, plus c. That my solution was going to be in the form y equals ax squared plus bx plus c. Well, y equals a is 3, b is negative 12, and c is 13. So there is my solution right there.